Chapter 25, we're going to be looking at areas under the curve. So this is the graph we want. Before we go anywhere, I need to know what this looks like so I know what my limits of integration need to be. And what I'm going to start out by doing is finding the zeros for this graph. I'm going to factor this cubic. After I pull an x out, I get a quadratic that factors into x minus 1 times x plus 3. So my zeros are at x equals 0, 1, and negative 3. Being that this is a cubic function, I know that it's going to be going upwards, a little squiggle, and then continuing up as it goes out to infinity. So here's negative 3, there's 1. This graph does something like that. And the area I'm looking for is this area here. So what I really need to do is attack this in two parts, because this part down here, that's negative area. I want total area. So I'm going to first take the integral from negative 3 to 0 of x cubed plus 2x squared minus 3x dx. And then I'm going to subtract, because the area is under the x-axis, the integral from 0 to 1 of x cubed plus 2x squared minus 3x with respect to x. And doing this integration, we get x to the 4th over 4 plus 2x cubed over 3 minus 3x squared over 2, evaluated at negative 3 and 0, minus the integral of that same thing evaluated from 0 to 1. And what we end up with is 0 minus negative 11 first integral minus negative 7/12 minus 0 from the second, and our total area ends up being 11 5/6 cubic units. If this were a question where we could use technology, we could think of this as being the integral from negative 3 to 1 of the absolute value of f of x. Now there's no way to do this by hand, but we can do it in our graphing calculator. So what I did here, I put into y1 that cubic polynomial that we have. I'm going to go into math. Down to the bottom, I'm going to select choice 9, function integrate. And on the newer operating system for the 84, we have this nice fill in the blank template. If you have a different calculator, you need to make sure that you know how to do this. But I'm going to put in negative 3 as my lower limit, 1 as my upper limit, and instead of having to type the whole function again, I'm going to go into this variables menu over to y variables, and I want a function variable, namely I want y1. And I want to integrate y1 from negative 3 to 1 with respect to x, and I forgot to put something here. I forgot to put my absolute value. So under math, I arrow over to number, select absolute value. Now I put my y1 inside the absolute value. I've got it punched in the way I need it. I push enter. 11.8 with a 3 repeating, that is 11 5/6 cubic units. On a calculator test, it's that simple. The second example asks to find the area enclosed by two functions. We have a line and we have a parabola. Again, I'm going to start with a simple picture, simple sketch of this. So x plus 2 that would be roughly that line. X squared plus x minus 2, I can quickly factor that, and I get x plus 2, x minus 1. So my zeros are at negative 2 and 1. And I could set the two equations equal to each other. X plus 2 equals x squared plus x minus 2. Solve this, I get x minus 2. That means that this quadratic is intersecting the line at negative 2 and positive 2. And what we're going to do, the general rule for this is we're going to take the integral of upper minus lower with respect to x. It's that simple. So I'm going to integrate from negative 2 to 2 of the upper equation. That would be the line, so x plus 2, minus the lower, that would be the parabola, and all of that with respect to x. I can combine some like terms, and what I'm really integrating is 4 minus x squared. 4x minus x cubed over 3, evaluate, and this equals thirds cubic units. Now we're going to come back to this idea of velocity and position. Remember that position function, if we take the derivative of that, we get the velocity function. So it stands to reason that we should be able to integrate to get back to the position function. And we'll do that in just a second, but we're going to approach this a little bit more intuitively. And to do this, we are going to integrate. So my position function, s of t, is going to be the integral, and I'm going to take the general integral. I'm going to anti-differentiate without any limits on here of t squared minus 3t plus 2. So my position function is t cubed over 3 minus 3 halves t squared plus 2t plus c. If I can find where I'm at after any given amount of time, I should be able to figure out how far the object travels in the first 4 seconds. So let's start out with the position when time equals 0. That equals c. The position when time equals 1. We get 1/3 minus 3 halves plus 2 plus c. That's equal to c plus 5/6. So at 1 second, I'm 5/6 farther than I was to start out with. The position, we get 8/3 minus 6 plus 4 plus c. So I have c plus 2/3. So now I'm 2/3 from where I started. We could figure this out too. I'm going to skip that one and find S sub 4, and I'll show you why in just a second. But we get 64 over 3 minus 24 plus 8 plus C plus 5 1/3. Let's look at how this particle is moving. I can stop at 4 because I only care about the first 4 seconds. But let's look at a sign diagram for the velocity. Let's set v of t equal to 0. And what we find is that we have critical values at t equals 1, 2. You should be able to get that by factoring. So if I go to a number line, starting at 0, here's 1, here's 2, and I check these intervals. I check something like 0.5. I find that the velocity is positive. It's positive velocity means position is increasing. After 1 second, it's negative. And then after 2, it's positive again. What does this mean? Well, what it means is that we're moving right. If we're considering our motion in a straight line, and then left, and then right again. So let's draw ourselves another number line. This time our number line is going to represent position. So here's time equals 0. We're starting out at C. And then we go this way until we hit 1 second. At 1 second, we're going to turn around, change our direction, until we hit time equals 2, at which point we're going to turn around and go to the right again, until we hit t equals 4. We don't really care about position at 3 because we've continued to move to the right this whole time. 2.5, 3, 3.5, 4 seconds. Let's look at how much distance we've traveled. This first leg of the journey, we have traveled c plus 5/6. The next leg of the journey, between 1 and 2 seconds, I've traveled a distance. Remember, this is total distance, not displacement. That's going to be the difference between where I am at the beginning and where I am at the end. So c minus 5/6 minus c plus 2/3. And now I have the third leg of my journey. That third distance is going to be the difference of where I am at time equals 2 and where I am at time equals 4. Time equals 4 is c plus 5 1/3 minus, to find the difference, c plus 2/3. And what we find here is that all the c's end up canceling, and we get 5 2/3 meters. Displacement that's just going to be, it's essentially as the crow flies, right? So what I need to find is I need to find s sub 4 and subtract s sub 0, the starting point. So minus c. So the total displacement is 5 1/3 meter. And we could verify these on the calculator just by computing these two integrals. And notice into y2 on my calculator I put in that position, that velocity function. And I'm going to integrate now from 0 to 4. And if I just put in my y2 variable here, think about what this is going to give me. Is this going to give me total distance, which we found first, or displacement, which we found second? That's finding displacement. 5.3333, that's 5 1/3. If I take that integral and insert my absolute value, that's going to find me total distance. Which we find to be 5 2/3. These calculations should be pretty straightforward for you. There shouldn't be anything crazy and new for you. This idea, drawing the pictures, that might be a little bit foreign. But the idea, hopefully you can follow what we did. That's all for now.